Welcome to the presentation of our paper titled EquiCaps, Predictor-Free Post-Aware Pre-Trained Capsule Networks at ICCV 2025. I am Athinoulla Konstantinou, and this work is a collaborative effort with Georgios, Leontidis, Mamatha, Thota, and Aiden Durrant. Self-supervised learning is built on invariance. Models use this property to learn common semantic concepts by aligning latent space embeddings of augmented views of the same sample. However, methods that strictly enforce invariance can discard useful transformation information, such as pose, which can limit their generalization. This motivates post-aware learning for novel view generalization and to equivariance, the central focus of this work, which preserves transformation information by enforcing input transformations to correspond to predictable transformations in latent space. Equivariance in self-supervision is typically enforced with predictor-based objectives with only a few works using architectures that are equivariant by design. In these predictor-based methods, the predictor is used to predict the target representation of the transformed view, given the original view representation and the known relative transformation. While promising, this yields ad hoc representations, depends on vanilla CNNs that are not naturally suited to encode equivariance and uses extra modules. By contrast, we propose to exploit equivariant architectural mechanisms, specifically capsule networks. This is since capsule networks use a routing algorithm based on agreement of part-whole relationships, structuring representations into capsules, with each encoding both an entity's existence and its instantiation parameters. Our approach directly exploits these biases that prior methods do not, yielding an intuitively controllable, interpretable latent space and a streamlined pipeline. We call our method EquiCaps, and it is based on a Siamese setup with a shallow capsule network projector. We employ the self-routing algorithm, a non-iterative approach, to reduce computation and adapt it so that each capsule outputs an activation probability vector that encodes the existence of a unique entity and a 4x4 pose matrix that encodes its rotation and translation attributes. To enforce equivariance, we multiply the pose from the first view by the known relative transformation between the views represented as a matrix and align the transformed result with the target pose from the second view with an MSE loss. Before alignment, each pose matrix is normalized by its Robitius norm. For invariance, we minimize the cross-entropy between activation probability vectors, and to avoid collapse to only a few highly active capsules, we apply mean entropy maximization regularization to the activation probabilities as well. Finally, we also apply the variance-covariance regularization to the concatenated activations and poses. The overall loss is a combination of these four losses, and importantly, EquiCaps architecture theoretically extends to any transformation which can be expressed as a matrix. We also introduce and release the 3D bench T, extended 3D bench, which includes only one geometric transformation, rotation, while ours adds translation, which increases task complexity. Our downstream tasks include classification as an invariant task and relative rotation, translation, and color prediction between pairs of images as equivariant tasks. Importantly, all pre-trained models are optimized only for rotation equivariance. We observe that EquiCaps achieves supervised level rotation performance on both 3D bench and 3D bench T while inherently capturing translation. In the scenario where both rotation and translation are optimized, EquiCaps maintains its superior geometric performance, and we similarly find that the non-capsule-based equivariant methods do not generalize well to multi-geometric learning. We also perform nearest neighbor retrieval and find that EquiCaps nearest neighbors best match the query image's overall pose, and only capsule-based methods retrieve the nearest neighbor with the rotation-matched pose. In this work, we introduce EquiCaps, a predictor-free, streamlined equivariant method based on capsules that gives the controllable, interpretable latent space. We also release an SC3 benchmark and show that EquiCaps achieves state-of-the-art rotation and translation prediction, with capsule-based models generalizing best to SC3 settings and in transfer learning, including object detection. Thank you so much for listening. Here is a link to our paper, to our code base, and to our dataset.